Good morning, everybody. Thank you for joining us for our webinar, Big Machine Learning with Physics and Data-Driven Modeling. Why understanding advanced analytics and machine learning is important for engineering professionals. Our webinar will be 1 hour long. We will have a 15-minute Q&A session at the end. So if you come across any questions during our presentation, please ask us, and we will be happy to answer those questions. I would like to get started with a brief introduction to our distinguished presenter. Dr. Ed Marotta is a principal consultant at Sierra Labs, LLC. He's also adjunct professor with the Mechanical Engineering Department of the University of Houston, where he teaches courses in the Subsea Engineering program and in data science and computational methods. He has received a BS in chemistry from the University of Albany and an MS and PhD in mechanical engineering with specialization in thermofluid sciences from Texas A&M University. He is a fellow in the American Society of Mechanical Engineers and an associate fellow in the American Institute of Aeronautics and Astronautics. Dr. Marotta has held faculty positions at the Mechanical Engineering Department at Clemson University and at Texas A&M. In addition, he is widely published in the area of thermofluid sciences and digital twins, and he holds numerous patents. With the intro out of the way, we will get started with our main presentation. Dr. Marotta, would you like to take over?
Okay, thank you, Beatrice. So I'm gonna share my presentation, hopefully, and I'm gonna go into presentation mode. Okay, so hopefully everyone can see my first slide.
Yes, we can. Thank you.
Very good. Okay, first thing, I want to thank Beatrice and Avias for asking me to give a presentation on this. This is a very important topic. I know that, and also like to thank you, the audience, for this morning, since I know you're all very busy in your jobs, but I believe this is a very important topic. It is the future going forward within the next decade or more. So, but it's quite interesting, really the presentation that I'm giving here, hopefully it's more on the educational side to motivate you to go out and learn and take courses, machine learning and AI, which will then ensure that you'll develop a new skill set. But again, what I'd like to be able to do here is just show you the benefits to engineers, why engineers should be interested in learning about machine learning, advanced analytics. You don't have to be a data scientist, but you can be what I call a citizen data scientist, someone who can converse with a data scientist. That's their specialization. You can ask the right questions, you can work with them and collaborate on a project, and then you as the expert, as the engineer, can make sure that whatever results that you get back from the data scientist makes sense, right? Because you are the subject matter expert. So topics that I will be covering today in general, again, the overall theme is, as an engineer, I believe that you should take the initiative and educate yourself in advanced analytics and machine learning. Maybe not so much in AI if you like, but that's a little bit more advanced. But definitely these advanced techniques of analyzing data and then using algorithms that are readily available to you, right? Because you don't have to write all these algorithms. You just have to be able to understand what is the insight, what is the value add that you're trying to glean from your data, and then choose the appropriate algorithms to run. Now you can do this in R, or you can do it in Python, or typically what I like to do is run these in Jupyter Notebook, right? Because then I can write Python code. But you also should take the initiative to learn Python or R. So quickly, I'll talk in terms of my goals and objective is really to demonstrate the value add of machine learning and AI to your work activity as an engineer, and then potentially show insights, again, that you can glean from data based from a model generation perspective, right? Because it's all about developing the model. And if it's the model, that means you have to be able to do some mathematics that one can then use to make some forecasting, which I call predictive analytics. And then from that, take actions, right, that are beneficial. So these are the topics that I'll go through. Talk a little bit about analytics, making it practical, transforming data to knowledge. That's the important thing. Can we derive insight and forecasting? And then I will talk a little bit about the history of digital twin, because it is a buzzword and there's a lot of different definitions. And so I'd like to at least talk about it. I'll give you my perspective on what a digital twin is. I'll give you my definition. You don't have to accept it. Everyone has their own definition, but I think the core content is the same. And then what I'd like to do is summarize with a slide that is a activity through ASME. It's a new task group that was formed through the Petroleum Division, where we're looking to come up with standards that one can write, or guidelines that one can use and publish for engineers, right? All right, so why advanced analytics and machine learning? This is where I'd like to start my talk, and then hopefully I can give you some useful example as an engineer, and hopefully you can appreciate where we're coming from and the importance. So the important thing here is a lot of people use the word or term big data. I'm not sure if that term is really useful to engineers. I believe that we have data that can vary in size from 1 megabyte to 1 gigabyte to 1 terabyte. And each of those data sets can, if you analyze the data correctly, if you can cleanse it, if you can aggregate it, and then apply the right model, you can glean some valuable insights, right? And that's the important thing, right? Where is the value add from your data? It doesn't have to be specifically on the volume of the data, right? It's really the quality of the data that you have to first assess, massage, and then apply to. But of course, as engineers, we like to forecast assets. So if you're a production engineer, many of the things that you're responsible for are different assets. One of the things that you'd like to be able to do is, can I predict or forecast a failure into the future? Can I then maybe determine the useful life that's left over, in which case then I have to decommission the asset? Can I then maybe schedule preventive maintenance so that if my asset goes down, I can minimize the duration time that the asset is down and increase what I call the availability of the asset? But to be able to do this, and a lot of people will say, okay, I need, if one is going to do real-time sensing and be able to use that data from sensors, typically on the right-hand side here is the useful information that we can gather from sensor data, right? And so in this case, they could be distributed sensing, right? They could be more than one input into your database, your data lake, and then from there you can take your data and then cleanse it, aggregate it, impugn it, and then from there apply the right algorithm. So we want useful data, and then from that useful data we want to apply the advanced analytics. And typically, if you're an engineer and you're responsible for a particular asset, you want to do performance condition monitoring, right? I think that's where the importance lies with respect to engineers, especially if you're a production engineer, if you're a process engineer, if you're a manufacturing engineer. That's where I think you will find the importance of advanced analytics and machine learning. But that doesn't mean if you're an R&D person or if you're a design person, one can then use advanced analytics to help you optimize your asset so that you can minimize the cost and other issues, let's say weight issues, right? You're trying to minimize. So again, using machine learning, advanced analytics, optimization will allow you to take sensor data, to be distribute, transform it into useful data, and then apply the advanced analytics, and then again, glean the useful info. So if I look at this, I always like to start with a definition. This is a definition of big data. Again, a lot of people in the industry really don't like this terminology of big data because, again, one can find insights and value add from data that can span the spectrum from 1 megabyte to 1 terabytes or more. But here's a definition that I was able to get from Gartner IT. It deals with high volume, high velocity, again, time series, high variety, meaning you're dealing with structured, unstructured data, and then you have to decide whether you can perform some supervised and unsupervised analysis that here brings about or informs and thus enables you to achieve enhanced insight. And then ultimately, this is why we get paid. If you like it or not, we have to make decisions, right? That's how we get paid. This is why we went to school. This is why you get a bachelor's degree in engineering or some technical field, so that you can take data, you can analyze it, you can model it, various assets, but ultimately you're getting paid to make a decision. But there is one particular term that they don't mention that I do want to mention here is veracity. Again, this fourth V in the big data deals with uncertainty of the data, meaning the quality, right? And so, as I have here in terms of these bullets, that there are particular aspects that many business leaders, maybe executives, do not trust information that they have to make decisions on. And I think a lot of that deals with the fact that quote unquote the data is of poor quality. You have to decide as an engineer, maybe as a citizen data scientist, what that means in terms of poor quality, right? And so, but this is a formal definition that's out there. It's good for us to understand it. But again, there are people who are pushing back on this, believing that, again, to glean valuable insights, you don't need high volume, you don't need high velocity, right? You may need a variety of data, whether it's, again, text, structured, unstructured data, but you don't always need high volume to make useful insights into the data. So again, for me, where is the next generation big data solutions are going to come from? And so I believe in the near term, challenges in the area of machine learning AI is to generate models that are as robust as possible, right? So accuracy is important. Define or glean useful insights, right? With value add. So I know I'm going to say that a lot. I'm going to say value add. If you cannot distinctly show that whatever you're doing from an analysis perspective is adding value, then you're just wasting your time. Then it just becomes an academic exercise, which I may be interested in because I like those kinds of stuff. But as an engineer, you have to report back to your boss, your leader, whoever that executive, and typically they're going to want to know, well, what where's the value add, where's the cost savings, where's the time savings, and so with respect to value add, it could be as simple as what I call enhancing engineering efficiency that leads to business outcome, which again is showing some kind of cost savings, or maybe some particular way of developing a new business model that will generate revenues. So as well, I believe that the next generation of big data solutions will come with the aspect that it has to be low storage, right? In terms of we can't always have a data lake. We can't always go to the cloud to be able to access the data so that we can analyze it, massage it, and provide insights. Many times, our models must run on devices, let's say, which I'm going to now call edge devices. And these edge devices are just computers that have a CPU or two. They're very low in storage. And so, especially if they're mission critical or they're safety critical operations, that time delay of going from the actual asset to the cloud, one cannot tolerate that. So maybe your model has to run right on the edge, and typically these don't have a lot of storage capacity, nor do they have a lot of CPU capacity, and so that's going to be important, right? Again, as a production engineer, you're going to be interested in condition performance monitoring. If you're a manufacturing engineer, you're going to be interested in unit quality and process yields. If you're a design engineer, you're looking to use machine learning or these next solutions from machine learning or AI. You want to come up with a design that is the most robust, reliable, cost efficient, and then optimum, right? One of the things that we always want to do is once we have a design, if we have a model, whether it's high fidelity or low fidelity, high fidelity meaning 4D, low fidelity, which is maybe 0, 1D, which I'll call that our reduced order models, right? We want to be able to run that through a optimization technique so that one can optimize a particular parameter. If you're interested in offshore equipment that goes subsea, weight is a huge consideration. So optimizing, let's say, a tree or a jumper or a flow line for weight optimization is important, right? Because if one can then reduce weight, it reduces cost and reduces other types of issues that, as an engineer, you have to deal with. So this is where I believe the next generation solutions are going to come from if we're going to make machine learning and AI valuable to the engineer. So I realize this is this is probably new to you, but then how do we transform data into knowledge? So one of the things about machine learning, if you look at a lot of the mathematics that comes from regression analysis, is that you'll get some type of polynomial expression. It can be linear or nonlinear. And typically, if you're developing what I call data-driven models, right? And this is where machine learning comes in. It helps you develop what I call reduced order models from data, right? Typically, you'll have a certain number of feature sets or parameters that you're inputting. And then when you're developing that function that enables you to transform inputs to an output, you're typically going to have weights, and I'm going to call these coefficients. And so if you've developed a linear and nonlinear data-driven model, then there's going to be coefficients in front of the input parameters that you're taking from sensors, right? And so over time, what you can do, if you do this continuously in terms of the time series platform, one can then take a look at these coefficients or these weights in front of these features. What can be done here is over time, one can then track how these weights change in three-dimensional space. And then depending, again, you can start from the origin. The origin can be at the point of commissioning of the asset, or it could be at the reset once you've done maintenance and you've particularly fixed a particular fault or failure that you've occurred. But as you're going through time and you're developing and you're using machine learning algorithms to develop these reduced order models, you're looking at these particular weights. One can look at how these are drifting in three-dimensional space. And you can see that I have three axes here. The fourth can be time, but how the various changes in the coefficients in three-dimensional space, how they track can help you indicate what particular failure is going to occur, right? And so one can take a look at the vector from the origin to the point where you're plotting that three-dimensional point. That particular arrow there can indicate to you not only the useful life of the particular asset, but how close you are to a particular failure that you can associate with that coefficient. And so this is how one can transfer knowledge or data into knowledge so that one can do failure analysis, looking at and forecasting potentially failures that can occur either a week from now, a month from now, or 2 months from now, right? And of course, your confidence in that particular failure is going to diminish as you're looking in time, a week, a month, or 2 months, right? And so again, probability is going to play a big role. So this is where I believe in, and I don't think too many people are doing this, is looking at how these coefficients change with respect to time and how we can predict failures. So here's an example where we can use analytics and it plays a role in modeling. What we're doing is we're taking the model, and this is again an adaptive model. It's from data, or it can be from a physics model, right? So we have a physical system, and there's various signals coming in from 1 to n, and of course you have the signal y, which is really your target value. And typically what you're doing is you're placing it, many times it could be a black box. Hopefully, if you understand the mathematics, again, that's why it's key to understand the mathematics behind these algorithms. Otherwise, it's a black box, like neural nets. Neural nets to me are just black boxes, where other types of regression machine learning, the mathematics, the equation. And so the key is, can I take continuously the feed from the experimental and then adapt the model so I can go from the left plot where I have a particular example here where I'm measuring displacement, and it's for a particular operation that we were interested in. We have the experimental data. We came up with the model, the simulated model. It could be physics or it could be data driven. And you can see that they're off, but that's because we haven't adapted the model. And after we've adapted the model, again, we're looking at changing the coefficients. We can get better predictions between the experimental and simulated. So again, this is where machine learning helps you develop what I call the reduced order model. It gives you the weights, and then on a continuous basis, some time scale that you determine, we can go back and run that particular model on new data, and then we can adapt the coefficients such that now the actual model is better predicting what we're observing. So again, it's really, we're interested here in looking at the magnitude of the change in the weights, and the magnitude and the direction as well, that provides the insights for not only forecasting, but then you can use this for preventive maintenance. Here's another example. This has to do with a rotary encoder for a gimbal for an offshore rig. A gimbal is located what I call underneath the spider, and the gimbal supports the weight of the drilling riser. It also accommodates for offsets and also acts as a shock absorber, right? But on this particular gimbal are encoders that help you determine not only the position, but also the shaft speed. And in this case, this particular system, and it was a system, had two encoders, had one on the left and one on the right, and we were looking at the shaft speed. Using data that we were gathering in real time, we were able to develop what I call a health indicator for both the left and right encoder that, based on how you read the coefficients, how they're changing, how they're being plotted, and then gleaning the insight from the magnitudes of those coefficients, one can determine whether or not a particular encoder is in a healthy state or is in a non-healthy state. So again, this is, I can't tell you the particular company that we work with for this particular example, but again, I can tell you it's a gimbal, it's an offshore drilling platform that we're looking at. Again, we were looking at real-time data. We're looking here at shaft speed, we're looking at position, and we're taking that signal, and from that, you can see how, respect to time, how the signals on the right-hand side for the left position and right position, depending on what's occurring, whether or not it's operating in a healthy state or non-healthy state, you can look at the plotting, in this case, the jagged plot here, and one can then determine if something is going to occur. So again, this is an example where one can take machine learning, develop that regression model, look at the coefficients. But again, the importance here to the engineer is, if you're interested in systems availability, this allows you to quantify systems availability. And of course, systems availability is based on reliability of the asset and also the availability, right? So those are important. Also, another terminology is maintainability, right? So all those are interconnected. So knowing the reliability, maintainability, one can then determine the availability. And those are all separate terms that are important to an engineer as it relates to an asset, right? And if you want to look up the various definitions, but I'll tell you one that I have is here is simply put, availability is the measure of the percent of time the equipment is in a operational state, where reliability is a measure of how long the item performs its intended function. And of course, those two are now related to maintainability as well. So again, this is where machine learning as an engineer will help you understand systems availability and reliability. So getting back to condition performance monitoring, again, this is what we're interested. If we look on the right-hand side, this is what most engineers do quite well, is that first bullet, right? We're very reactive, right? This is done today, but what we need to do, I believe, and this is again where education plays a key role in educating yourself in this field and making yourself feel comfortable, is that we want to get to the predictive maintenance part of it and then the prescriptive. So predictive meaning that we're looking at a system, we're monitoring, and then hopefully we can predict an impending failure. And then based on that, we can potentially diagnose what the problem is. And then from that, we can make recommendations so that we can minimize whatever impending failure or any particular operational parameters that are causing the system not to operate at its optimum or healthy state. So you can go around this, right? Again, the goal is to minimize operational costs of structures and assets and improve availability. We can do this from analysis. We can go from information, descriptive analytics, where we're taking the data, we're developing trends, we're looking at the trends, we're on a daily basis or hourly basis. If there's something that is about to occur, we can We can use some diagnostic analytics, use the analysis. We can make some predictions, and then from that, we can apply our prescriptive analytics to basically answer the question, what should I do about it, right? So this is where we want to get. We want to get to predictive maintenance, and then, of course, we want to get to prescriptive maintenance, especially if we're interested in automation, right? If we're going to automate a process, then we want to be able to have a closed loop where if you're predicting a failure, then you can automate the actual remedial action that needs to be taken to fix whatever particular issue that is occurring. Again, so why analytics in terms of education? Well, on the right-hand side, I talk about sensing, analysis, prediction. Ultimately, these are the steps that we want to take as engineers, right? And ultimately, in the end, as we take the sensing data, we do the analysis, we make the predictions, it gets back to making smart actions or smart decisions. And so without the ability to bring in advanced statistics, advanced analytics, machine learning, I don't see how you can do this in a very efficient manner. I don't see how one can easily in real time analyze streaming data and then make predictions that you can particularly forecast an impending failure, and then come up with a root cause identification so that one can then take corrective action. Again, this is where educating yourself, it's not that hard. There's lots of master's program. You don't have to take master's program. You can take certificate programs, or you can take workshops as well. And that way you'll get you'll get the fundamental understandings of the techniques. And some of them, like my course, my 1 or 2 day workshop, I'm actually giving you the code. I'm actually giving you the Python code via Jupyter Notebook for all of these techniques. And all you have to be able to do is understand them, the background of when to use them, how to use it, and then how one can then cleanse the data and make the data useful. Again, how do we derive value, insights, and forecasting? It comes down to, as an engineer, I know we like to think about it in terms of components, but we have to elevate ourselves. So we have to elevate ourselves to what I call systems engineering, right? Or model-based systems engineering, right? And this is where analysis, using some of these high-fidelity computer models, such as Fluent or Abacus from a finite element, Star CCM from a CFD. This allows you to do high-fidelity modeling, but then what you want to do, if you want to then take it from a component basis to a systems basis, right? You need to reduce it from a higher fidelity to a lower fidelity, and you're able to then interconnect all of these models together. So now you're looking at a systems, right? And then for each component or subsystem to an overall, what I call system of system, you're going to have a model. All of these models are adapting, and they're all interconnected, communicating with themselves, right? It's this ability to do this that allows you to have fault detection, forecasting, prognosticate, and then from a fault detection, it could be a leak, it could be seal wear, it could be erosion, it could be other types of faults that allow you to make the right decision in terms of action that needs to be taken. On the right-hand side, from forecasting and prognostication, I think ultimately from this, what we want to be able to do is determine useful life. What is that remaining useful life, right? And so this is what I believe, having the knowledge of machine learning and AI itself leads to systems thinking. And I think as engineers, we don't do enough of this, right? We need to think about systems engineering and look at it from a requirements perspective, performance requirements perspective, right? How how do we know, or how, when do we know that our particular system is not operating in its optimum condition, right? I will give an example of another industry where we're looking at machine learning to develop a digital twin to look at it from a systems perspective. So of course, many people will talk about data science. People will talk about data analytics. What is artificial intelligence, machine learning, and what is deep learning? And of course, they're all interrelated, right? It starts with data science. Under the umbrella of data science, there's data analytics. Under data analytics, under that umbrella, there's artificial intelligence. Under that, you're trying to simplify things a little bit. Maybe you don't want to use neural nets or CNN or RNN, or these multi-hidden layer neural nets. You just want to be able to use some machine learning techniques that don't involve a black box. You want to understand the mathematics behind it. That's machine learning. And then from that, one can then glean deep learning. And of course, deep learning there is the way I've seen it, and the way I've seen definitions, is just a subset of machine learning. And usually people use this term, they're actually referring to deep artificial neural nets. So as an engineer, it's important that when we're talking about data science, that there's different umbrellas, different aspects of data science, and where you play, where you want to play in this is really determined on the role that you want to take, right? We're not all going to be data scientists, which basically means we're not all going to be unicorns that have an in-depth knowledge of computer architecture, coding, and then mathematics, right? We're not all going to have very deep knowledge of statistics and such. But as engineers, we can use machine learning, and we can apply the right algorithms. We can maybe understand some of the mathematics behind it, right? But we don't have to go in and try to provide proofs, all of these particular techniques that we're wanting to use. And that's where mathematicians come in, right? They're interested more in deriving proofs than there are in really applying the mathematics so that it's beneficial to an engineer. Also, it's important to understand the difference between business intelligence and data science. And so I have two columns here. The important thing is, if I look down the column of the business intelligence, to me, business intelligence is really backward looking, where data science is really forward looking, trying to predict what might happen in the future. Again, business intelligence is trying to analyze the past and guess the future, where in data science, we're predicting the future in real time, and then we're advising. So as an engineer, it's important that you understand the distinction between business intelligence and data science, and where machine learning and artificial intelligence plays in all this. And so if you look now on the right-hand side, on the vertical axis, I have degree of effort, and then in the lower one, I have what is the activity that one would perform here. Of course, we always have to start off with acquiring the data. And so that itself may take a lot of effort or may not. It also depends on whether or not you have a sensor set that is correct. If you have a correct sensor set that allows you to predict what you're trying to predict in terms of failure, it's fine. If not, then you have to go back and determine what is the right sensor set, what are the right input parameters that allow me to predict the right outcome by which I can then make decisions. And then once we acquire the data, you can see that the degree of effort increases here, right? This is where the veracity of the data, the uncertainty in the data, being able to cleanse it, look for missing data in your data set. Can I aggregate the data? Can I impute the data so that can I then determine, let's say, from an unsupervised perspective analysis, what are the key feature sets or features or input parameters that are giving me the greatest significance or providing the greatest significance in terms of the effect on the output. So this again is where you as an engineer should be playing a key role in understanding your role and maybe working with the data science or even the data engineer, right, to ensure that the right data is being prepared, acquired, and prepared. You may have to, from the particular features or input parameters, you may have to take some kind of combination. This is where I call you're aggregating the data. So from a particular two inputs, you may come out with one where you're trying to normalize it. This is aggregating the data. This is where, as an engineer, I think it's important that you understand this process, and then taking that from a degree of effort and analyzing the data, determining what is the right algorithm to use. Do I want to look at unsupervised techniques or supervised techniques? What type of clustering techniques do I want to use? Do I want to use k-means, x-means, or there are also some other clustering techniques which are all unsupervised that involve some Gaussian parameters where we're looking at the data from a Gaussian perspective, so that when you take the data and let's say that the data itself combines in very distinct clusters that may or may not be circular. Let's say if you have elongated data sets, how does one use these techniques to be able to cluster the data? And can I also glean some probability that the data actually belongs in that particular cluster? And so there are various techniques that one has to be aware of and apply the right techniques. In fact, the example I can give you here is I advise for a startup company where we're looking at electricity consumption from retailers, your home. And what we're able to do is take time series data. Typically, if you're interested in consumption, this is electrical consumption from your home. If you actually look at your bill, they'll only give you data on a monthly basis. But if you're really interested as an engineer and you want to become a citizen data scientist, you can sign up with Smart Meter Texas. And from your smart meter, you can actually get data not only on a monthly basis or hourly basis, but you can get data consumption on 15-minute intervals. So that particular time scales opens up a lot in terms of applying machine learning techniques to provide insights that will allow you to, based on your lifestyle, your home, the number of occupants in your home, your settings, you can take that data at that particular time scale, and we can determine, based on prior models, what consumption is due to your AC, what consumption is due to lighting, appliances, heat pumps. We can also determine whether or not in the wintertime, right, if you go home, if you're sleeping at night and you want to use a heating blanket or a space heater, we can see that, right? We can see the peak in that consumption. And so can we now take that time series data and use machine learning to bring insights in terms of not only helping you minimize your consumption, maximizing your cost advantage, but also we can take that data, historical data, and we can tell you what particular plan is best for you. Because as you know, in Houston, there's a lot of, it's unregulated. And if you really look out there, there's over 125 plans out there by different providers. And so one can then take data and go through this process, and we can determine or help you determine what is the best plan for you, and then give you insights in terms of minimizing cost. So again, this is where, as an engineer, you can take machine learning algorithms, artificial intelligence algorithms, and you can apply it to everyday life. And this is real life applications, right? This is something that's costing you money. So through data science, what we're trying to do is we're trying to answer questions, right? And so typically the process that we, as engineers using data science, we want to be able to describe, discover, predict, and then advise, right? And so under the discover, basically, how do I develop the understanding of the content of my data? Again, this is where this descriptive analytics, plotting and trending allows you to understand the content of the data. And then through discovery, again, through descriptive analytics, and even predictive analytics, what are the key relationships in the data, right? And so it's the data-driven models that one develops from machine learning techniques or AI techniques that allow you to discover relationships in the data. And then, of course, from that, we want to be able to predict likely future outcomes. And as part of that, is really under the discover part of it, is diagnose the problem, right? Can we, once we're able to predict a particular failure mode is going to occur, can we diagnose that problem? And then can we advise? Right? What is that course of action that I should be taking? And so on the right-hand side, I just list in bullet form some of the more key techniques out there that we're interested in maybe using, or the outcome that we're interested in ascertaining, right? Of course, you know, we have to deal with multidimensional data, meaning that our model is also going to be multidimensional. But again, many of the parameters may not be that significant. And so then how can we go from a multidimensional correlation to something that is only relevant to maybe one or two or three parameters? And so this is where techniques such as PCA, which is principal component analysis, or singularity, or singular variable decomposition, this is where one can then identify through these techniques what are the key parameters that one needs to key on as an engineer that allow us to make the predictions and then make the recommendations and such. But of course, we're interested in time series. A lot of it has to do with sensors that are coming online. How do we deal with time series data? There's also recommender systems. We may not be too keen on this, right? This particular aspect of machine learning has been applied in terms of making recommendations for movies. Once you've have a large enough database where every particular moviegoer will rate the movie from 1 to 5, one can then use these types of machine learning systems, these recommender systems, to then, based on your preference, make recommendations in terms of, let's say, maybe up to 5 or 10 different movies that are similar to movies that you've viewed and that you've either rated very high or very low, right? So this is one particular application of recommender systems, right? And of course, optimization is also important, and carrying out simulations is also important as well. So in terms of real applications, it's not only within oil and gas. I'm assuming that a lot of you are in oil and gas. You don't have to be. machine learning is being carried out in aerospace, avionics, satellite thermal control, manufacturing. Again, quite important here in being able to apply machine learning and also applying your engineering knowledge to ensure that whatever outcome that is being predicted makes sense, because ultimately you are the subject matter expert, and so you're the one who has to ensure that the outcome from the prediction makes sense. But of course, there's a whole host of real applications. I think I gave you one already when we're looking at energy and feedstock and utilities, where I'm applying these techniques for power usage in terms of analytics. We can use analytics for carbon emission and trading arbitrage. One of the things, if you're in the energy space in terms of electrical, providing electricity to suppliers, you're interested in arbitrage, knowing when to buy and when not to buy future supplies, so that you can maximize your profits, right? This whole concept of smart gridding, right? Again, the only way that you can do this is as an engineer, as an analyst, applying machine learning and all of these tools that allow us to achieve what we're trying to achieve. So it is being applied not only in oil and gas, but in sustainable energy, in wind farming, automotive, manufacturing, ensuring that the quality at each particular station, that particular unit is meeting the requirements, right? The functional requirements. And if not, then one can then put a halt and ensure that you can take the remedial action that's needed to ensure that quality is back online, right? So there are lots of other opportunities out there to apply machine learning as an engineer, right, as well. So let's talk a little bit about digital twin, which is something that is being used here as a buzzword. I think some perspective, some historical perspective on where this term came about is important. I do give a definition. Again, this is my definition. There's other people that are looking at definitions that apply to their particular applications. I know the various operators from Chevron to Exxon to Shell, they're holding 1-week workshops just for them to define what it means, what a digital twin means for their particular business model, right? So here I define the digital twin. Again, it is a virtual model. It's a virtual model of a process, a product, or service. So a product is an asset. A process can be something like corrosion, if you're interested in corrosion in pipeline, or erosion in pipeline. One can then develop a digital twin process that can help you predict when a particular pipeline or elbow in a particular pipeline is about to bleed through, right? It can also help you determine where to place sensors, right, for a useful life monitoring. Services, here I'm talking about back end, right? All the logistics that one needs to bring to bear if you're trying to maintain availability of a product, where maintainability is also making sure that a particular fault is going to occur in a particular time period. What you want to be able to do from logistics, from that digital twins based on logistics, you can order the right part, right? You can look at the vendor that supplies that part. You can look at which vendor gives you the best cost for that particular component, its availability, and then ensuring that you have the right crew there at the right time so that you can minimize that particular time period that that asset is down. So again, it takes the physical world, connects it through to the digital world, but you do it with digitized data. And so the person that I give credit to that had first published this in an article is Dr. Greaves. And again, he was more interested from a life cycle perspective, from a PLM. And of course, he was doing this when he was working as a summer research fellow at Johnson Space Center, and he was working with a NASA engineer. And it's really the NASA engineer who actually came up with that coin of a digital twin. But of course, Dr. Rees took it from there, applied it from a systems engineering perspective, right? And then, of course, with the advent of present day machine learning, software analytics, artificial intelligence, this is where I think the advantage of the digital twin comes in, right? It's the advent, the integration of these techniques that allows us to take data, creates a living digital simulation model that one can update continuously, and then since it will change, right? These models have to be adaptive because as this particular asset, process, or service, as you're going with time, right? That asset is going to change due to fatigue. And so the model has to be able to adapt, right? And be able to understand the physical change in its counterpart, which again is the physical asset. So this is the brief digital twin in terms of its history, where it came from. It's been around since the early 90s. Again, it's not new. It's been around. How we're implementing the terminology, the digital twin, to ensure that we get useful insights as engineer, and that it provides engineering efficiency or enhancing engineering efficiencies in terms of processes or services. This is where the integration of what my talk is today, and educating yourself as an engineer, maybe becoming that citizen data scientist, will allow you to develop that digital twin and being able to understand the benefits that come from a digital twin, right? So one of the areas that I've actually used or had an idea of where we're using digital twins is in sustainable energy wind farms. And so out there, each turbine has its own digital twin, right? One can develop a digital twin for each turbine. The key here is going back to my systems engineering thinking as an engineer. Not only should I be thinking about the individual turbine, wind turbine, and its digital twin, but I should be thinking about that digital wind farm, right? It's the ability to virtually represent each turbine and looking at individual interconnection or relationship among the various wind turbine that allows you to increase the overall efficiency of the wind farm and not maybe the individual turbine. So it may be that through that digital twin, and that digital twin is connected to another wind farm, and it has this digital twin, and they're communicating with each other, that it may be telling, based on wind conditions and stresses on the blades, that, hey, I may have to detune myself, but by the fact that I may not be running at my optimum conditions, that it may allow you, digital twin in the background, or wind turbine in the back, it may allow you to run more optimally so that the overall wind farm can increase its efficiency. And so GE has used this concept of wind farm, this digital wind farm, to not only look at each individual wind turbine, but looking at the entire wind farm. And of course, GE Aviation, they have digital twin for their engines. And all these digital twins are just data-driven models, right? Some of them are based on physics, but mainly they're all based on data-driven models. Each and every time an airplane takes off and these engines are running, they have sensors that are collecting. Every time they land at a particular airport, all that data is dumped in some server somewhere, and then that data gets analyzed. And so it's through maybe one or two sensors that data updates that digital twin, that model for that particular jet engine, to understand the reliability and availability of that particular jet engine. And so I think this gives them, and maybe Pratt & Whitney as well, the ability to be competitive against other manufacturers. So there are examples of digital twin where now we're connecting them in terms of what I call the digital system of systems, or some people might call it the cyber-physical systems, right? Where you're looking at multiple systems, subsystems, and then you're connecting them, and then you're trying to optimize the overall system of systems. From a architectural perspective, I'm going to have to go a little bit quicker now since I only have another 25 minutes. From a architectural perspective, there are different swim lanes. As I show here, from left to right, from visualization, prognostication, intelligent decisions, and decisions to optimizations. Right? Underneath that, there's a layer that we have to worry about, which is cybersecurity. We have to understand what are the data standards, and this is again where professional societies like ASME and SPE can, maybe API and such, other societies can come in, and even operators themselves or manufacturers have to come up with standards by which data can be transmitted, and then how do we communicate among the various IoTs or edge devices to a cloud server so that one can achieve what you would like as an engineer, right? But there are different swim lanes. I particularly think of them as different digital twin. You can have a digital twin, which is just a CAD drawing, right? You can have a digital twin, which is dynamic. So that CAD drawing there is a static. I would call that a static digital twin. About the only thing that you might be able to do with a CAD drawing is look at interference and tolerancing, right? But it's not very dynamic. So then you want to go to a different flavor of a digital twin, where it's now dynamic. You can place inputs and you get an output, right? You can simulate. It's adaptive. It's learning. You can make predictions. Then you can go into the diagnostics, and then from a controls perspective, you want to be able to have that prescriptive analytics where you're making recommendations, feed it back to a closed loop controller that will take actions without a human intervene. But that doesn't mean that a human should not be there monitoring and ensuring that it is the right action to take. The human should never be, the expert should never be out of the loop, right? They should always be in the loop. But again, the fundamental building blocks here are data-driven models, physics-based models, or a combination of the two, which I call hybrid models. And this is where machine learning, artificial intelligence, maybe taking running high fidelity, finite element or CFD models and 4D, and then being able to use the correct mathematics to go from 4D down to 1D or 0D, right? That allows you to minimize your computational expense in terms of hardware, and you also don't have to worry about the computational expense in terms of time, right? Because these reduced order models, these digital twins should run and should adapt quite quickly. So let me give you something that is a little bit more advanced. This is something that I'm quite interested in terms of, this is where the advance in machine learning comes in. And in particular, if you're interested in time series data, there's a particular branch of machine learning called Gaussian process regression. So what is a Gaussian process regression? Basically, instead of coming up with one particular function that takes your inputs and then potentially gives you an output, and then worrying about that particular accuracy, what Gaussian process regression does, it uses Gaussian statistics, it uses Bayes' rule, and it comes up with a family of functions, which I call a distribution of functions. And you can see on the right-hand side, what I'm showing here is a family of functions that could potentially be the function that you'll use to help you forecast and make recommendations. Again, it's all based on assuming that your data that you're inputting follows a Gaussian distribution. And so if that's the case, then what I want to be able to do is have a Gaussian distribution of functions that could all potentially be the solution that will give me my desired output. And since I really know nothing about these solutions, I have to make an assumptions, right? What is my prior belief in terms of the mean and the standard deviation? And so typically, when you're dealing with this, you're assuming that, or your best guess for the knowledge of the function of, or the output of these functions is the mean and the standard deviation. And typically, you'll choose the mean to be 0. And then, of course, you'll decide whether you are interested in 1 standard deviation or 2 standard deviation or 3 standard deviation. So this is your prior belief based on these distribution of functions. And so you may ask me, how do I generate these functions? Well, there's various kernels out there, right? There's several different kernels. In essence, these kernels are just a covariance matrix. So it allows you, it takes a covariance matrix, and from that, it gives you the functions that can potentially be the function that will give you the correct answer. So how do I go from all of these functions to functions that I'm interested in? Well, this is where now you take your training data, and on the right-hand side there, a very simple plot there. I have for a particular data that I know. This is my training data. And now, once I have my prior belief, and I go through Bayes' rule, now I can get, or I can determine the posterior Gaussian process. And so I can throw out those functions in my distribution of functions that do not go through my data points, my training data points. And so now what I've done is through my training, I've eliminated a tremendous amount of functions that really glean no insight. And then, of course, right at the data point, the uncertainty or the standard deviation is very, very small, right? Because my function goes directly through that data point. But as I move away from that data point, it gives me insight in terms of what is the uncertainty of the prediction between the data points that I don't have. And so that's, as an engineer, it's important to understand what is my working envelope, right? And it's through this technique that allows you to determine through these process Gaussian regression, what is the particular uncertainty in that mean, because that black line that goes through my data point is really the mean prediction of all those distribution of functions, right? And so then it gives me an idea of what the uncertainty is of that mean prediction away from my known training data point. So how did I use this? I've actually used this technique for what I call upstream data. And so this is actually real-time data where I'm looking at it from a time series perspective. And you can see that I'm looking roughly at about 10 or 12 hours worth of data. This is real-time data. And you can see that there is a maximum value that the data is indicating, is slightly above 200, right? But this is real-time data that has been employed as a time series, you can see that the data is quite jagged. So something's occurring in the data that's causing that particular value to deviate from its nominal condition, which I would say here for my data is slightly above 200. So my question is, how do I use advanced machine learning, in this particular case, Gaussian process regression, to help me determine that function that allows me to not only predict my training data, but then go forward? And so I've actually used this particular technique. And so on the left-hand side, I'm actually taking roughly 42 minutes of upstream data, applying this machine learning technique called Gaussian process regression. There's multiple kernels that I had to bring in. So the key here is, how do I combine the various kernels or these mathematical expressions that gives me the coefficient matrix, so that I can predict the mean value going not only through my training data, but then can I use that and then predict forward? And so you can see on the right-hand side, what I've done is I've used roughly 45 minutes of upstream data with a 95% probability to predict 4 hours into the future, right? So again, I'm only showing you here roughly about 4.5 hours. This data actually goes out to 12 hours, right? So what's interesting here is on the right-hand side, what you're seeing is in blue, scatter plot is the actual training data. The blue line is really the mean value going through that training data. And then I'm using my ability to forecast out to 4 hours. And then you can see what that prediction or the mean prediction is, along with the uncertainty in the prediction. And then what I've done is I was able to then plot the real data, right? And then I can then judge how well my model is predicting. And so overall, it's doing, I think, a good job, except that there are particular points, roughly at slightly less than 11.5 hours, where my model is not picking up those data points. So something occurred there that could be or couldn't or can or cannot be an outlier, right? So something has occurred that wasn't anticipated. And so one, that maybe you can use that as a outlier detection, or something has happened, right, that has caused the operation to move away from nominal conditions. And so how do I know it's an outlier? Because look, I have the probability plot in gray, right? So something definitely has happened, right, outside of my what I can see or perceive to be my window of operation. Okay, so this is one of my last slides. As an engineer, you have to understand that data science, machine learning is a contact sport, right? You have to also, you have to be into the weeds, right? You have to be able to understand and work with that data scientist, become a citizen data scientist, or maybe a data engineer, right? But it is a contact sport, right? You can't just sit back and think that you're going to absorb this and understand it unless you're actively involved, right? And so you have to immerse yourself. But I think it's important as well that you as an engineer have to also justify the business. What is the business problem? And then you also have to be able to be flexible to modify your goals as the business models evolve, right? So if we look towards the end there, right, you may have to build multiple prototypes, and you may have to get those prototypes. In this case, it could be the models, get them out there quickly in front of the user. And if they're bad, you want to fail quickly, but you want to fail forward. And failing forward means that I'm learning from my failures. So if you're going to fail, you want to fail quickly, but you want to fail forward, meaning that you're learning. Again, the important thing here is value, right? you need to identify from the very beginning what the uplift is as part of the project from the start, and then be able to isolate the impact of data science and enable the workflows that allow you to develop model-based um, predictions, right? Or validations. And then one can then develop these models based on historical data. So there's going to be historical based validation or value that's being brought. But again, as an engineer, if you're going to get involved in this, yeah, this is a contact sport, but each and every time you have to understand you need to show value. If you can't show business value, then you shouldn't be involved in this, or at least, again, if you're interested from a academic perspective, it's great, but you need to show value. So why is this important? So I'm going to take the last minute or two, and then I'm going to open up to questions. So why is this important, and why am I, giving these types of lectures and trying to get the message out to engineers that it's important for you to educate yourself in machine learning, but take it from a perspective of an engineer. And so I've been asked to chair a task group under ASME, under the petroleum division, to come up with a roadmap by which ASME can develop guidelines, standards that deals with the topic of big data and digital transformation. So this is an initiative, but as we look at the timeline, so we've had our kickoff meeting. If we look at the timeline, I'm trying to bring in an agile perspective where I'm not going to wait 2 years down the road and then come out with a guideline or a standard or some educational course by which engineers can get PE credits. But I think it's important that we develop documents that one can show, put it out to our customers and get their feedback, and then be able to modify it. So as part of this, in the first 4 to 6 months, we've divided the task groups into 3 subtask groups. One group is commissioned in terms of coming up with common terms and a glossary of big data in the digital world, so that we can all speak the same language. Right? There is a lot of confusion with respect to big data and digital transformation and its terminology. So it would be nice, and I think there's, we're not trying to start from scratch. I know there's other people working on this, so we want to, especially societies, and so we want to be able to take learnings from them and then collaborate with them, and then hopefully collate everything into one particular guideline and such. Another particular sub-task group that has been formed is to really show the value add to the industry, right? What are the particular examples, not only in oil and gas, but in aviation, aerospace, automotive, manufacturing, where we can actually show value add by the implementation of the use of machine learning and AI to not only, let's say, enhance engineering efficiency, which then translates into cost, but also we can demonstrate improvement in safety. Because safety is one of the key pillars of anything that we should be doing as engineers. And so showing that we can bring value to the industry through the use of machine learning and AI is important. And then, of course, developing various guidelines and standards, and coming up with a roadmap, which this particular roadmap is just a straw man that we've put together. And of course, this is going to morph. But I think in the end, what we like to be able to do as a society, especially ASME and other society, is conduct seminars, summits that talks about big data and digital transformation. But then at the same time, can we develop educational courses that engineers can use as PE credits, right? And then do this on a continuous basis. So again, as an engineer, this is my final say on this. because I am at heart an engineer, even though I do teach. I've taught engineering, but I am an engineer, and I want to show that whatever I do adds value to the community. So with that, I'm going to end it. So.